All right, a little bit provocating title, I think, and I heard already some discussions afterwards. Sue just telling me, are we out of work? And I hope to guide you through a number of things, and at the end of my talk, so maybe to say already a little bit where this is leading to, I will, of course, come to the conclusion that we are not out of work. So. Problem solved, we can relax, still many more years to work on. This is work which has been done partly at ABB, but I will just show a few examples and then guide you through what we are currently doing at my chair of fluid dynamics at TU Berlin. I will talk about modeling of thermoacoustic instabilities, then move on to non-linearities and talk a little bit about control and move then on how we can use, for example, linear stability theory in order to predict and to understand in more detail thermoacoustics. So it's somewhat adding a few different views on what just Tim Lewin presented to you. Of course, this is not only my work. There's a number of people involved, like Sebastian Schimek, who is also here, Jonas Mörk, Steffen Terha, Kilian Oberleitner, Bernhard Schosic, Bernhard Bobusch, Katharina Göckler, Lothar Rukes, and many more, to just name a few. So this is kind of collaborative work we are doing in Berlin. So the thermoacoustic problem, I think you are all aware of it, but just let me quickly present this to you, although I'm sure that you know already a lot about it. You have unsteady heat release in your combustor due to equivalence ratio fluctuations, flow turbulence, flow instabilities, and that leads to the generation of sound wave associated with pressure and velocity oscillations, and they may again perturb the flame. And if they are in phase with the pressure oscillations like Rayleigh described already, and if this integral view of P prime times Q prime dt dx actually is dA is larger than the flux across the system boundaries and larger than the dissipative losses, then you get kind of a feedback instability, a growing instability. And that can lead actually to damages in the combustor. Although I'm always hearing when I show this slide, actually this figure here is taken from Tim Lewin. If you talk to people in industry, they say, well, combustor damages we don't have anymore. And I'm sure about this, that probably you can work around it, but what definitely is still an issue, and that leads me maybe to part of my answer whether thermoacoustics will still bother us in the future, is that of course it somewhat limits your operating cycle. So you have to run your combustor in operational types where it is stable, and this is not necessarily the best for your emissions. So you have always this problem that you have a draw-off between emissions and pulsations. And I generally show this nice slide where you have, and we don't have anything to draw here, we have this curve on one side, the pulsations, on the other side, here on this side, the emissions, and on this side, the pulsations. So if you have high emissions, then generally your pulsations are low. If your emissions, you want to get to low emissions, then you can generally get high pulsations. So this is always the draw-off you have here and the problem you are facing. And it actually increases with two-day gases. So if you go to hydrogen-rich fuels, the problem might increase to syngases and so on. So the deterioration of the system performance is definitely an issue, although system failure due to combustor damages are obviously not occurring that much with the understanding we have today. This is just presenting one typical example of a premix system as being used by Alstom and Siemens, a swirl stabilized burner where you inject your fuel here you have your combustion air entering to these 2 slots or maybe more slots, depending on the burner system you have. This creates a swirling flow. You inject your fuel along this entrance for your combustion air, and this is then being mixed, and the swirl is generally so high that you get a phenomenon which is called vortex breakdown, which is actually associated, as you see here in this slide. This is also a swirling flow in a tube, and you see also this phenomenon of a vortex breakdown. And what you see here, this is dye inside, that you get a strong recirculation zone in the center where this vortex breakdown occurs, and this is being used to stabilize your flame. And of course, as you see here, I mean, this is flow stabilized. You might have all kind of instabilities forming on this and influencing actually your flame dynamics. And this is what I'm going to talk then about. Also, liquid fuels are definitely a problem, and I will also address this very shortly and very briefly in my talk as well. So this is the general setup, and you might have different designs of burners, but the principle is more or less similar. So you need to stabilize your flame. You have some kind of recirculation zone. Either you create this by swirl, by vortex breakdown, or by some kind of recirculation zone behind obstacles. So same principle. This is the problem also on old slides, but it's still very nice because it explains a lot of features I'm referring to later. And one of the problems is obvious. You see here the flow. This is CFD simulations, large eddy simulation. And you see here a picture of the OH chemiluminescence of the flame. And what you see here is fluctuating heat release on top and bottom. And this is caused by some kind of helical instability, a precessing vortex core. And I will talk about this later, how this is actually formed and how we can control that precessing vortex core. The thing is that this precessing vortex core causes heat release here at this side and 180 degrees later at the upper side, and vice versa. So it's an asymmetric heat release fluctuation, what you can see. This specifically occurs at frequencies often which are not associated with the resonances, or which are associated actually with evanescent modes. So it might not propagate in your combustor, but it also occurs at higher frequencies, and then it definitely can lead to resonances in your combustor. The axisymmetric thing is shown here. This is what we generally talk about. You can see here the flow under a strong forcing amplitude, and this causes the vortex breakdown to fluctuate. It causes all kinds of structures to form, and then this strong axisymmetric heat release, which leads to these combustion instabilities, what we always discuss. So coming to the modeling, and this is just kind of an introductive thing also, because you probably know already a lot about this, but going back to my first slide where the thermoacoustic problem is solved, leads maybe also a little bit to this issue. So generally what we do is that we do a full 3D acoustic model of the gas turbine, and this we combine in some kind of network model where we have the main thing in the flame response, because you can model everything very nicely in acoustics, but the flame response is the most difficult thing. And this is being then combined in some kind of a network model, and out of this you can perform stability analysis, and if you have a nice analytical model which includes also your nonlinearities, you can predict your even your amplitudes in frequency spectra. There's a number of approaches also to get parameters for this flame transfer matrix, from steady CFD analysis as well as from time-dependent CFD analysis, and they all work more or less good, but they are all very time-consuming. The measurement procedure And I think this has been established when Wolfgang and I started actually to work, and together also with Bruno Schürmans, is as such that you model your system by up and downstream running acoustic waves in your combustor. And this here is the so-called describing flame transfer function, scattering matrix. And plus, in order to, this describes the connection between the up and downstream traveling waves upstream and downstream of your burner. And in addition, of course, your burner generates noise, and this is these two additional parts. So if you want to solve this problem, then you have only two equations, as you see here, and you need to create independent test states, which you can do under atmospheric conditions very nicely using, for example, loudspeakers downstream and upstream of your flame. This works nice. It's a difficulty to get this, for example, under pressurized conditions. And this leads me now to the question, is the thermoacoustic problem solved? We applied this to a real gas turbine, and you see here a very complex gas turbine, a GT11N2 with a silo combustor, all kind of different acoustic modes, so highly three-dimensional field in here, and still it was possible to model this. And the problem was there that the amplitudes actually in this combustor were too high at certain operational conditions, and therefore the question was, how can we damp them? So what was done, this engine was analyzed using the scheme I described before. This is the modeled data, the red curve, and the blue curve, the engine data, fits very nicely. So you could say, problem solved. Well, unfortunately, it's not always the case like this, but we come to this later. However, also another nice example then was, how can we control this? How can we damp the instabilities? And if you look here at the burner distribution, so this is the hood of your, where all the burners are placed, of your engine, and you can see here all these blue parts are Helmholtz dampers already. And then you see this instability here, and you would say, well, okay, let's design them in a different way and move them to this frequency. However, these Helmholtz dampers here were designed actually to damp this instabilities. So if you would move damping power to this instability, this would result in a high amplitude than at a higher frequency. So it does not work. So the idea at the time was, when I was responsible, I had this idea, well, let's replace burners by dampers. So we replaced a few burners by dampers, and in the limit, you would replace all the burners by dampers, but this is, of course, not the solution, right? I mean, this would not help us, and you could not get any more energy out of it. So also there, limited damping power. And in addition, as you all know, that the efficiency of a gas turbine depends also on the pressure loss in your combustor. You cannot just increase your velocity, your burner velocity, because that will increase your pressure loss of your combustor, thus decrease the efficiency. So not a solution. So we had to come up, we could only replace 3 burners, and just by redistributing them, knowing the three-dimensional pressure field, we managed actually to damp the amplitude here by more than 50%. So this was quite a success. This was the modeling. Again, look at the red curve, and then a colleague of mine went to the engine side and placed actually the dampers in there, and also the result, the engine data, was even looking better than what we predicted at the time. So very nice results. So this shows you a little bit what the problem is and where we want to go. And now we need to understand better what kind of additional problems we are facing. One, for example, is oil combustion, or all kind of funny fuels with a lot of hydrogen content. We know how to model the transfer function from atmospheric conditions, atmospheric pressure conditions, to high pressure conditions when the burner is operated with natural gas, with methane. This works quite well. But as soon as you have liquid fuels, then your spray you form here in your high pressure combustor is giving you a problem. It is pressure dependent, your spray formation. Therefore, you cannot just repeat these experiments at atmospheric conditions. In addition, if you go to hydrogen, then also the properties depend very much on your pressure. So this is a problem. And as you see, this is a much more complicated setup. It does look very different from our atmospheric pressurized test rigs. And it's not just so easy to place a number of microphones upstream and have a long tube to measure accurately the pressure distribution and calculate out of this the acoustic velocities. And you cannot do the same downstream. And in addition, how do you excite this whole thing? It's very, I mean, you cannot just use a loudspeaker under 30 bars of pressure or 40 bars of pressure if it goes to aircraft engines. So one of the ideas was to use optical methods, but also there you can, of course, use the OH radical as one element, and you know that the OH radical is responding to equivalence ratio fluctuations, but at the same time is also responding to mass flow, power fluctuations. So it is reacting to both. So the problem is, if you have both in your system, you cannot just analyze your system. So we built, and this is actually a project we were carrying out together with Alstom in the framework of AG Turbo. We built a siren which helped us to excite the flow under high pressure conditions. Actually wide frequency range, 0 to, well, almost 0, but up to 400 hertz, pressure amplitude, the maximum air mass flow which you could use here was 1.5 kilograms per second. So this was almost 50% of excitation depending on the boundary conditions or on the operating conditions. It allowed for inlet temperatures of 550 degrees and a maximum pressure of 40 bars and a sinusoidal excitation in this frequency range. And that was being applied. And as I told you, the purely acoustic method is obviously the best because we exactly know what is coming out of this. And if you use only one signal, here in this case, for example, the OH chemiluminescent, the OH radical, then you see a lot of discrepancy with respect to the pure acoustic method. And this is because you are capturing all the effects in your chemiluminescent signal, but you don't know where it is coming from. So the idea then we had together with Bruno Schürmanns was to use more signals actually, and if you do so, then you can see by using more signals and even combining it eventually with the acoustics, you get a much, much better agreement with your signal. So this is now, I would say, not yet state of the art. There's a number of unknown problems, like for example, soot which darkens your windows, and also the question of how much actually is radiated from the soot. So there's still a number of problems with respect to liquid fuels, but for example, for gaseous fuels under high pressure conditions, this works very nicely. The other question is nonlinearities. So if we have our linear tools, then we can predict the combustion instabilities, we can predict the frequencies, but we cannot predict amplitudes. And actually, at the end, a company is interested in predicting pressure amplitudes because that could be used as an input signal for a life cycle analysis, for high cycle fatigue analysis. If you know the excitation amplitude, you can at least try to perform and to try to estimate how long will your combustor live and what kind of amplitudes would you even allow. I mean, just knowing that the combustor is getting unstable is not enough because it can actually oscillate at a small amplitude, which is not leading within the operational frame to material fatigue or to big disaster in your combustor. So you need to know the amplitudes. And if you want to do so, if you want to know what you can tolerate actually in your combustor, this means including nonlinearities. And this is being somewhat demonstrated here in this graph. You can see here a plot showing the pressure pulsations and here the time. And you can see here that an instability starts to grow until it reaches a finite amplitude, the limit cycle. And if you look at this graph, this is exactly the case. This is the squared oscillation amplitude, p prime square. This is generally what we call the loss in your combustor. It increases with the linearly with the pressure square amplitude. And this is when your amplitude actually experiences, your amplification experiences nonlinearities, and generally you have here reached a stable limit cycle, and this is where you would get your amplitude out of your simulation then. You can have also other kind of instabilities, but I mean, even worse things where you have an unstable cycle limit. You can see here you need to force actually your burner to reach this point, and actually if you are beyond this point, it starts to grow again and reaches then this stable limit cycle. So to do so, to investigate this phenomenon, we built a special test rig in Berlin, and this special test rig allowed actually for the excitation of very high amplitudes. We have here a number of loudspeakers, huge loudspeakers to give the high amplitudes, but in addition, this whole thing acts as a trombone. So like on a trombone, you can move this part outside, and doing so, you change your resonance frequency, of course, and if you operate your loudspeakers at your resonance frequency, then you can excite very high amplitudes. We also use preheated air, so it is very much aligned to real combustor conditions, and then use again microphones upstream as well as downstream in order to measure the acoustic properties here of this burner. And here are some results. These are actually taken by Sebastian Schimek. This gives you the flame describing function. So we are looking at the OH radical normalized by the excitation amplitude. And this is showing you, this is shown as a function of the frequency. And you can see that with increasing amplitude, your amplification goes down, so leading to a limit cycle. It's a non-linear response. If we look at this, just plotting here the excitation amplitude, and again here the OH radical, the chemiluminescence signal, then we see that at some kind of excitation amplitude here, about 20 to 30%, the flame is not being amplified anymore. So I can increase my amplitude, but nothing is happening anymore. Plus, we also see that the phase actually shifts with increasing amplitude. And if we look at the flame pictures, then you can see here phase averaged chemiluminescence images at one frequency. So this is excitation at 128 Hertz for different excitations levels. Here we have 9%, 27%, and 61% excitation level. You can see the influence of your flame. You see here this ringling, the effect of the excitation on your flame. And the stronger the excitation amplitude becomes, it resolves even to a detached flame, so the flame floats somewhat off your combustor at these high excitation amplitudes. And this is actually also then the conclusion for this specific case we looked into. We saw that the high amplitudes led to a shift in phase and average flame position movement, and the limit cycle in this specific case was due to a temporal extinction of the flame. So I'm coming now back to another system where we also look at nonlinearities, but we look at an azimuthal distribution in annular combustors. So in this case, this project is somewhat trying to simulate an annular combustor, but also looking at the very basics. So I will tell you about this in a second, what exactly we did here. But in order to model these kind of instabilities, let's face it, first of all, what can we do? It's a challenging problem, although we see that for some cases we can predict very nicely actually our spectra, but we have flows, we have flow instabilities, we have chemical reactions, we have acoustics, and we have a large range of length and time scales. And you can try to use detailed models, like, for example, large eddy simulation. Even if you want to predict the acoustics, you can do it compressible, but it's very expensive. And although we see that, like at Surfax, they try to model full combustors, it's still a very, very expensive thing and taking a long time actually to come to results. Low order models are more efficient, but then you need an accurate description of the flame dynamics. And this is, for example, what we can get from flame describing functions, from measured to flame describing functions. So in this case, we tried to simulate a very simple case, 8 flames in an annular arrangement, actually calculation by low order models, a measured transfer function, and the acoustic measured transfer function going in. It couples with the acoustic field. There's no flame-flame interaction. And this was also simulated not by having an annular combustor with 8 flames, but we did so by having an annular Riekel tube. So having 8 Riekel tubes distributed around the circumference, giving us similar results. But I'm concentrating only on the result here for the combustion case from the simulation. And what we see here is, again, the system runs into a limit cycle oscillation. So the system is generally unstable. And what you also see, if you look at the circumferential phase distribution, then you can see there is actually a circumferential phase distribution. There's not a fixed phase, what you would expect. And this confirms somewhat results we got actually from Bruno Schürmann's thesis a couple of years ago already, where he showed that the azimuthal waves you create in annular combustors are generally not standing waves, but travel around the circumference. So this we could prove by doing the simulation and by showing it also from this annular Riekel tube. And this shows you how this flame responds and so on and so forth. So this is what you typically see in full-scale engines. So the standing wave pattern is unstable, but what you generally get is that you get a moving mode around the circumference. Coming now to combustion control. How can you control these oscillations? And I'm showing we have hundreds of examples of combustion control, and there's a number of things which are important. First of all, it's what is the actuator you use. And I'm just talking today about some very simple actuators where we actually try to modulate the fuel. But this is also the most limiting factor, because your actuator has to oscillate in the range of 100 cycles per second over a long time, and this no actuator survives. So what we do today is we are looking into actually actuators which have no moving parts, like fluidics valves, for example, where you have no moving parts, but you can still excite your fuel flow or your airflow and thus try to control your thermoacoustic instability. So just to show a very simple example, we can also, of course, use acoustic excitation. Generally, what you do in terms of acoustic or in terms of combustion control is that you measure at the reference plane your pressure fluctuations, but you can also use the signal from a photomultiplier, feed the signal into a controller. Then you have to have a control scheme, and then you actuate either on loudspeakers or on the fuel flow, on a valve which modulates the fuel flow, and try to suppress the instability. And just to show you what you can do with this, this is actually an extremum seeking controller, so it operates at small fluctuations and tries to go to via these small fluctuations, tries to find the minimum actually of your pulsation. And this is here without preheating, but let's concentrate on the preheating case. This is the case without control, very high instability, almost 160 dBs, and applying this control you go down to 110 dB. So 150 to 110, 40 dBs less. So very, very significant suppression of your instability. And you can also use your model you have for your combustor, because one of the main problems is what happens, for example, if you change operating conditions. Then you would like to have a model which describes the pulsation behavior of your burner. So here we used as the model we used was based on the transfer function we measured before. And also this model based predictive control actually got us a very nice suppression of our instabilities. For example, this is a pure proportional control, so operating, just feeding a signal into your controller and applying a phase difference and thus suppressing your instability. And the model predictive control works much better, much more effectively. And having this in mind, we can actually apply these techniques to do something really nice. One of the problems, for example, is that in test rigs, you always have different acoustic length. So different acoustic resonance frequencies. So you do a test, for example, in an atmospheric test rig, and it pulsates, for example. Then in a company, you would go to a high-pressure test rig, and there it might be stable. And then the discussion is, well, what should we trust more, the high-pressure test rig or the atmospheric test rig results? And generally, preference is given in favor to high-pressure test rigs. And then what often happens, then you place the burner into your combustor, into the engine, and then it pulsates. And the question is why? The answer is because you have different acoustic boundary conditions. So an annular combustor differs in its acoustic boundary conditions from the test rig. So what you would need to do is actually to adjust your combustor always to the different acoustic boundary conditions. For example, by just placing a longer exhaust tube to it. But that's not that easy because your burner is being operated in different types of engines. Also, you see, of course, in an annular combustor or in a silo combustor, all kind of different modes. And then you need to model them all. So the idea was to dig a little bit more into this and have a system where we actually can control the acoustic boundary conditions here. And to do so looks very complicated, but what we did in this case was that we reconsidered our multi-microphone method, which we use in general to assess burner properties and transfer functions. And we applied this in the time domain so that we can actually destruct downstream and upstream traveling waves in our burner system in our combustor in the time domain. And that was then being applied to the following case. So this is our test rig. The burner is somewhere here, and the burner creates downstream traveling waves. They are reflected by the general acoustic boundary conditions, and in addition, we can generate actually a wave here by, for example, using a loudspeaker. But we tested also other actuators which are more usable, for example, for high-pressure test rigs. But in this case, I just present you the results for the loudspeaker. So we need actually a signal to superimpose here on these boundary conditions, like is shown here, linearly superimposed, in order to modify our transfer function. And that leads then to this control function which we need to apply in order to create a reflection coefficient which we would like to have at this end. So for example, you would like here, this is generally an open end, we would like to impose here an open, a closed end condition just by excitation of this loudspeakers. And that we applied to this case. So what you see here is, this is actually the pressure amplitude as a function of the frequency. In this case, we have an open end. This gives us a high and strong feedback, or we apply an orifice at the end. I'm not sure if you're familiar with this technique, how to damp acoustic waves, but often we use just orifices at the end of our combustor. This is a very simple and though efficient change in your acoustic boundary conditions. Very nice damping you can obtain this. There have been a number of publications by us and by others where you can see that an acoustic wave running into an orifice with a through flow creates actually, this acoustic wave creates vorticity, and this vorticity finally dissipates, and that damps your acoustic wave. So you have no reflection. You can almost avoid the reflection. And the reflection coefficient is shown here. This is the reflection coefficient over the frequency of your orifice. So in the order of 20% reflection, so a very small feedback only to your combustor, and a very simple method. This is the open-end reflection. It's not completely one because we have all kind of stuff there mounted at the exit of our combustor, so it's not a measurement error. If we dismantle the test rig and take away all the loudspeakers and all perforations we have at the end of our combustor, this is actually one and behaves very nicely like theory from Levi and Schwinger or others showing you this reflection coefficient. And then, so this is the two cases. In the case of an open end, you get full reflection. If we place this orifice, so reflection coefficient smaller, we get no response. And now, what we did is we applied the technique I just described you and prescribed with our forcing system on the case with the orifice a boundary condition which should correspond to the open end. And you can see that you get your strong pressure pulsations again. So the boundary conditions were still the same. This was the orifice. But now we use this forcing mechanism in order to apply this, open-end reflection coefficient. And you can see that your amplitude goes up. And of course, then you can modify not only changing it from open-end, closed-end reflection coefficient and so on, but you can also impose different lengths now. And this is shown here. By making virtually your combustor longer, you can shift your frequency, your resonance frequencies to lower frequencies and vice versa. So using this technique allows you to virtually modify your acoustic boundary conditions. So to go from an open end to a closed end combustor, from a non-reflective end to a reflective end, or from a reflective end to a non-reflective end, and also change virtually the length of your combustor. And this allows then for testing of different burners, of different burner behaviors in changing acoustic boundary conditions. So that is the basic idea behind this. And now I'm trying to get a little bit more deeper into the analysis of swirling flows. So you have seen a lot of experiments and a lot of results how we can actually get transfer functions, how we measure transfer functions under high pressure using different techniques. And now we try to dig a little bit deeper into the flow properties. And as Wolfgang said, this is also our hobby. I mean, we are the chair of fluid dynamics, so we like to look also in depth into the flow. And this is actually a very clean experiment. You can also design these experiments much cleaner than in a combustor. This is a swirling jet. And this swirling jet is being analyzed by either hot wire anemometry, and you can see here multiple hot wires because we are not interested only in the axisymmetric mode, but we would also like to see what happens to higher azimuthal modes. We can change the swirl number of this jet, and in addition we have the possibility to excite actually this jet. And the excitation mechanism is described here. So it's not only exciting axisymmetric, but you can excite also azimuthal waves using this array of loudspeakers. And the basic idea is also an old one, because what you actually can do, you can do beautiful things by this excitation of jets. For example, if you excite an axisymmetric jet, not a swirling one, unfortunately works not there. I can also explain you why, because we did the analysis on this. But let's assume an axisymmetric jet, and you apply different mode forcing. So for example, a helical mode -1 and a double helix +2. So spinning modes in different directions. Then your jet becomes out of the circular axisymmetric jet becomes a triangle. So you get a different shape of your jet. Or combining a -2 with a +2 gives you a rectangular jet. So you can modify your flow features by this kind of excitation. And we had this basic idea, maybe it works also on swirling flows. There it does not work, but there fortunately other things work. But this basic idea was great because we thought, well, you can, for example, use this technique to improve mixing. You know that a triangular jet or a rectangular jet has better mixing, is less prone to thermoacoustic instabilities. So the idea was just by forcing it, because it's not easy to modify a nozzle or to put into a combustor a rectangular nozzle or a triangular nozzle. That's not easy. There's always this story, Effie Gutmark says, I'm not sure if it's right or wrong, but the story was he was going to GE, and they had a problem with thermoacoustic instabilities out of a round nozzle, a jet out of a round nozzle. And then he took this nozzle and used a hammer, and then it became elliptical, and he placed it in again, and then the combustor was quiet. Not sure if the story as such is correct, but we actually tried also helical, we tried elliptical nozzles, and they were actually more quiet than the round ones. So anyway, looking at the flow features, this is a jet emanating at a very low Reynolds number. So you can see nice structures, and you can see already here that somewhat you have this delay, and this leads to this helical mode, which I just described you. But of course, this is not the Reynolds number we can work on. You can identify structures from here, but this has nothing to do with reality. In reality, we are at much higher Reynolds numbers. So let's look at a Reynolds number of 20,000. Well, then it's hard to distinguish any structures, or can you still see structures? I can't. So this is where we need to apply our techniques. And one of the things is that we try to decompose the flow into three quantities: the mean flow, stochastic turbulent part, and a coherent periodic part. And in addition, of course, you can also decompose this in different modes, so also in azimuthal modes, by having measurements from eight hot wires, for example, around the circumference. And out of this, you can gain phase and amplitude, and you can determine then the azimuthal wave number and so on. And what we try then to apply on this flow field, on this decomposed flow field, is a linear stability analysis. And this linear stability analysis describes you when a perturbation you put in the flow is unstable, this means grows, or is stable, this means it decays. And the basic principle, just to describe this very quickly, is that you perform this classical perturbation decomposition here of your coherent velocity signals and pressure signal. And this is done then in spatial direction, axial direction, and time direction, as well as in the mode, so in the azimuthal mode. And then you use generally an Sommerfeld type equation with a dispersion relation, and you solve this differential, this eigenvalue problem, this differential equation for complex alpha and real omega. And this alpha then, the complex part, the imaginary part of your alpha, gives you your growth rate. So this is the principle of this technique. And this again, we try to apply to this swirling jet here, emanating at a Reynolds number of 20,000. So we perform, in this case, different things in order to analyze the flow. One thing is that it's unfortunately not the best resolution I see here, but what is shown here is we get out of this PIV data, we perform a proper orthogonal decomposition to give us the most energetic modes. This is one idea, and this we do in the longitudinal plane as well as in the plane rectangular to your exiting velocity. And out of this, we try to reconstruct then the flow field. And we do a similar thing using the stability analysis, which I just showed you, and we get out of this a similar picture with using the POD modes, and use this also to reconstruct actually our flow field. And what happens then is that the reconstruction of this looks like this. So you already get a little bit more inside, and you can better understand what is happening. But I don't want to get too much into detail into this, because that has been these data have been processed by another group in Berlin, and then this beautiful picture comes out of this where you really better understand what is happening. And this is the swirling jet. This is out of experimental data. Again, this is not a simulation. And what you see here is this vortex breakdown. This is the vortex breakdown. And out of this vortex breakdown, shortly upstream of this, you have this helical instability forming. And this actually acts as a pacemaker for this helical outer mode. So this helped us to basically understand what happens in swirling jet. And just to tell you a few examples, I didn't bring all the results with me. For example, by exciting this at an azimuthal wave number, you can move the location of this vortex breakdown. So this is a wonderful feature, how to control the flow in the vortex breakdown location in swirling flows. So having this technique in mind, we looked at another thing, and this has been presented now at the Asymptope Expo in San Antonio. Why does non-uniform density suppress the precessing vortex core? This again, I think I can skip, but what we generally see is here that we have, this is a flame, this is taken by my colleague Jonas Merck, showing you again what I showed you at the beginning, and there we come back to the beginning, to the movies I showed you. This precessing vortex core, or the helical instability, how it sheds vorticity and instantaneous or different heat release at this side, and 100 degrees later at the other side of the flame. And what we often see is that we see this in swirling flames, but for some cases, it's being suppressed when we turn on the combustion process. And we wanted to understand why. And again, we target this problem using linear stability theory. And there I want to not to go too much into depth, but to tell you a few keywords so that you better understand what I'm talking about. So generally, we heard today from Tim that we can have instabilities which are convectively unstable. So you excite, for example, in a shear flow, in a jet, a small perturbation, you put in a small perturbation, and this is being convected downstream with your flow, and if it's unstable, it starts to grow. And then after a certain distance from your nozzle where you exit, it reaches its linear stability limit, and then it starts to decay. You can influence actually this kind of instability. This scales entirely with the shear layer thickness. So by modifying, for example, your shear layer thickness, making it a little bit thicker, the instability may reach the highest amplitude earlier and start to decay earlier. And this is, for example, being used in many applications. Like, for example, if you look at car mirrors and so on, they have like little vortex generators on this to thicken the shear layer and thus move the unstable motion where you get actually resonance of your mirror, the fluid instability away, the highest amplified mode away from your resonance frequency of your mirror, so that at 100 kilometers per hour your mirror does not vibrate and you cannot see anything anymore. So this is a known technique. In addition, this is generally for jets. If you have a wake-like profile like we have in our combustors, because we have the strong recirculation zone induced by the vortex breakdown, in this case, the flow can get absolutely unstable. So this means you put in a small perturbation, and in this case, if you turn off that perturbation, it would not grow anymore. It would just decay. There's no perturbation. But in this case, you start initially a small thing, and then it grows in time and remains almost constant in terms of the spatial distribution. So it starts to grow by itself and not convectively. And if you would put, for example, here in this profile like some kind of a blade or some kind of a feedback, like your a car window. So if you open this, you hear this strong hammering of the flow instability, then your flow might also get globally unstable. So this does not depend anymore entirely on the flow features, but more on the whole configuration. And we are interested actually in this globally unstable motion. By the way, this helical instability, the precessing vortex core, is a globally unstable mode. So if I turn back, this mode which you see here, this helical mode, this is a globally unstable mode. And then, as I said, we would like to look into this. So again, same applications. I think I just said this, so I can go over it. But now what we want to do is we need to look at the global mode, at the global instability, and therefore we need to identify where actually our omega is larger than zero. This would be an absolute unstable flow at the location where we get saddle point. So we need to look at both conditions. So what we do is we take our mean flow and we measure also the mean density. We perform a linear stability analysis on this, and based on this assessment, we get our local and global instability modes like frequency, growth rates, and so on. So we looked at two types of flames. It's the same combustor, but in one case, we added a lot of steam to the combustor, and that led to a completely different type of flame. This led to an annular flame, and in this annular flame, we have a precessing vortex core while in the V flame without steam injection, so steam injection 0, we have no precessing vortex core. All the other boundary conditions were the same speed, same swirl number, and so on. So no changes here. And if we look at the two flames, then you can see here the differences. This is the annular flame, what we call the annular flame, and this is the V flame type. So here in the annular flame, by adding a lot of steam to our combustion process, in this case I think 20 or 30%, I don't remember, 30% steam, mass percent of steam, we have a detached flame, we have no reaction near the nozzle. In this case, the flame is attached to the nozzle, and we have a larger inner recirculation zone, as you see here, and the main reaction takes place in this inner shear layer and not in the outer shear layers like indicated here. If we look now at the density differences, you can see here that this is normalized densities, that we have high densities in this center body wake. So this is this movable block burner with a center body, which we used here. We have large gradients in the outer shear layer, and the burnt hot gases do not go into the full wake of the center body. While here in this case, you see here a strong recirculation, so the hot gases can actually penetrate into the wake, into the region near the center body. So we have strong density gradients in the inner shear layer. So this is important. Strong density gradients in the inner shear layer. In this case, no density gradients in the inner shear layer, but in the outer shear layer. And if we analyze now the instability, then you see here the results of this global instability analysis, and you can see here the imaginary part, and as long as it is larger than 0, your flow is unstable, so you get the precessing vortex core, and from the real part of your omega you can predict the frequency. So this is 2 pi, so this corresponds then to a Struan number of 0.11, and the maximum you see here is about 1 diameter downstream of your nozzle. So in this case, you get the precessing vortex core, and now, and this results actually in this behavior, in this oscillating helical mode. If we now look at the V flame, then we see that this density strongly affects the instability. So this is a cold jet. Again, the same instability. It shows us that this helical precessing vortex core is being amplified. But if we turn on the flame, then our omega naught I, the imaginary part, is smaller than 0, so it is stable. So there is no precessing vortex core anymore at this frequency. So it's the density gradient actually which makes this vortex core to disappear. So a number of results here for this specific case is that this precessing vortex core is caused by a global instability. We could use linear stability analysis to predict actually the frequency, shape, and the source of this precessing vortex core. And we see also that density gradients may dampen the precessing vortex core. And I showed you 2 different flames where this actually happened. And again, going back to nonlinearities, but now trying to use actually also linear stability theory to address this and to assess why actually we have nonlinearities in a completely pre-premix system. So we have no equivalence ratio fluctuations, and we would like to look at the case what happens, what dampens actually this instability. So generally, you have multiple saturation mechanisms. You have, for example, velocity fluctuations, and you have equivalence ratio fluctuations, and as I showed you, they act on the flame response, and you can get instabilities due to this, and in the limit cycle, they are limited, for example, here that the equivalence ratio fluctuations cause partially extinction of your flame. And we would like to look more at this part. What causes actually saturation for our velocity fluctuations? So the velocity fluctuations, as explained, are amplified in your shear layer. They form while they grow in your shear layer large-scale vortical structures, and these large-scale vortical structures are associated with higher turbulence. They affect the flame shape and so on, as Tim showed us before. So you have an influence of these vortical structures on the flame response. And doing so, the larger these vortical structures become, they may also distort the mean flow field. And as I explained to you before, if you modify your mean flow field, for example, by making your shear layer thickness, increasing your shear layer thickness, you can influence these instabilities. And the same happens if you have unstable vortices. They get amplified, and as a result of the amplification, you take energy from your mean flow, and this broadens your shear layer. This is the basic theory behind it. And now looking at the flame response here at one excitation frequency, axisymmetric excitation in this case, around 200 hertz for different swirl numbers, and you can see, okay, already here we see an influence. Depending on the swirl number, I see different saturation behavior. So, for example, at a small swirl number, this black curve, you see saturation much earlier coming and not and pretty abrupt already at a small excitation amplitude. And this somewhat gets influenced then by swirl number. Why by the swirl number? Because the swirl number, again, modifies your mean flow field. If we look at the forcing amplitude then, then we also see that the forcing amplitude modifies our mean field. So what you see here is the mean flow field, and on top of this, you see the flame again measured by the chemiluminescence. And you can see that the flame shape is changing and the mean flow field is also changing. So now the question is, what do these coherent vortices do? And if we look at the coherent vortices in this case, and compare this against the phase average heat release rate, it seems to be pretty much, I mean, at least qualitatively, there is some kind of relation between the vortices as well and the phase average heat release rate. And if we plot the coherent kinetic energy, so this is just the integral over the amplitude u tilde square r dr, and plot this versus axial distance, then you can see that the perturbance actually growth in your shear layer reaches an amplitude. This would be, I mean, this is actually the case where you get linearly stable, and then the amplitude decays with further downstream distance. If we look at the coherent kinetic energy here and try to divide the coherent kinetic energy by the forcing amplitude, then this gives us some kind of idea of the amplification. Because if the ratio between the coherent kinetic energy and the forcing amplitude is larger, you get a larger amplification of your perturbance, which you give into your shear flow. And this is exactly here the case at a small forcing amplitude. So what you already see in this figure here is that with increasing forcing amplitude, this is the forcing amplitude, you go to almost, you go to this saturation, because here at 1, your amplitude which you get out is the same as the amplitude what you get in. So you get a saturation, the higher your amplification, the higher the forcing amplitude is. And now, if we look at this case for different swirl numbers, then we can see that for lower swirl, we actually get a stronger saturation than for the higher swirl. This is maybe not that important, but now looking at the flame response again, this is the flame response as a function of the forcing amplitude. Here plotted normalized OH chemiluminescence for different swirl numbers. This is what you have seen before. And if we plot the coherent kinetic energy, there is again significant similarity between the flame response and the coherent kinetic energy. So this suggests actually that the saturation mechanism is coming from the saturation of the flow amplification. So we put in velocity fluctuations, they are amplified in the shear layer, form these structures, and so on. So if the forcing amplitude gets higher, then the shear layer amplification becomes smaller, and therefore the influence on the flame would also decrease. And this actually we try to display in this figure. So you can see here the triple decomposition. This gives us the coherent part of our vortical structures, and this actually is the result from the linear stability theory. So this is measurement, this is prediction. Of course, this is not as a nice result. I mean, there is some differences, but the case is the measurement here is much more complicated. This is in a combustor, and what I showed you before, these nice pictures from this helical instability was just in an unreacting, unconfined jet. So here you have much more things which influence this data, but still the agreement actually is quite good. And if we perform then look at the saturation effects again coming out of the stability analysis, we see a very similar behavior when we compare this again to the plot, to the contour plot of our coherent amplitude. So with increasing excitation amplitude, the amplification decreases. Here we have strong amplification. The ratio between the resulting amplitude and the excitation amplitude is large and becomes smaller with increasing excitation amplitude. This is from the stability analysis, and this is from the measurement, still in very good agreement. And this is the same thing for different swirl numbers. So we performed this for a number of cases just to prove what we were doing there. I think basically showing you again the same results. So to summarize, this result is that our velocity fluctuations form large-scale vortical structures. They act on the flame response. If we increase our forcing amplitude, the amplification here gets lower. We modify the mean flow, and therefore the influence on the flame is less. And we can do the same thing actually by using linear stability analysis and calculating this whole effect. So this leads me to my first question again. And this is somewhat also the end of my talk. So is the thermoacoustic problem solved? Well, I believe a number of things we did already, and you have seen a number of results where thermoacoustic analysis and control was successfully applied. But there's a number of open questions still, and it's still a very interesting field. Like, for example, applying different tools, looking at nonlinearities. We don't know what is happening at higher pressure yet. There's still a lot of analysis needed. We need better prediction tools, specifically if we want to scale to higher pressure. And then the question, of course, what happens at different fuels, for example, with a strong hydrogen content, liquid fuels, and so on. There's still a lot of question marks. Thank you very much.